Hi there, I'm going to talk about how to use shear cell testers to optimize the flowability of powders. Quick outline of my talk. First of all, I'm going to define flowability, discuss fundamental properties, and show you how shear cell testing measures fundamental properties which you can use to predict flow behavior of powders and design equipment for reliable flow. So what is flowability? There are different definitions, different metrics. Here are some of them: angle of repose, car index, car ratio, Hausner ratio, FFC, which is a flow coefficient, Flodex, which tells you how long or if a powder will flow through an orifice or funnel, and flow energy, which is popular with Freeman Technology FT4 testers. They all have one thing in common: none will tell you whether or not your powder will flow. So, what is good flowability? Well, this is good flowability. You have a hopper, you open up the gate, and material flows. That is good flowability. What is poor flowability? That's when you open up the gate and nothing flows. This material has poor flowability. Nothing flows. So the definitions of flowability should be rather straightforward. All you're trying to do is prevent an obstruction from developing. So obstructions to flow include arching or bridging, and that can happen when the arch that naturally forms at the outlet of a hopper is so strong it will support its own weight. Sometimes you'll find bridging a hopper. In Boston, where I live, you can have a hopper and a bridge. Rat holes can be even worse because at first you think things are fine. You open up the valve, material flows, but after a short while, it stops flowing. You look inside and you find that you only had flow right above the outlet and you have a lot of material left behind along the walls, and we call that a rat hole. So whether or not you have a flow problem often depends on what type of flow pattern you have inside your bin or hopper. And there are two types of flow patterns: funnel flow and mass flow. Funnel flow occurs when the hopper walls aren't steep enough or low enough from friction, so you don't get flow on the walls. And if the material is cohesive, you can get a very large rat hole that occupies quite a bit of the bin but does not empty. What you often want is mass flow. So mass flow is taking place when the hopper walls are steep enough and low enough in friction so you get flow everywhere. So you can see how much better the flow behavior is. You get nice steady flows, predictable. You get first in, first out. In the event that you get sifting segregation where the particles separate from side to side, you mitigate it. You don't get rat holes because the rat holes cannot be stable because the hopper walls are too steep and have too low friction to support them. So how do you avoid flow problems? Really straightforward. You want to make sure the outlet is large enough. And if possible, you want to formulate for mass flow or select or design a mass flow hopper. But what you need is your powder flow properties. So these are the fundamental flow properties: cohesive strength, internal friction, bulk density or compressibility, and wall friction. Obviously, if you know cohesive strength, it seems like you'd be able to determine what size of the hopper outlet you need to prevent an obstruction from forming. And what might be subtle is the bulk density. Remember, we're trying to allow gravity flow, so it seems like if we have a lot of weight, the powder will flow more readily through the outlet of a hopper. So bulk density or compressibility is important. And wall friction, of course, is used to determine the hopper angles that ensure mass flow. If you have a hopper wall material that has high friction, it makes sense that you would probably need a rather steep hopper wall to get flow on the walls or mass flow. Whereas if you have a wall material that is low in friction, you'll probably be able to get away with a relatively shallow hopper angle to get flow on the walls. So who figured this out? Andrew Janicki, my hero. Andrew Janicki is a pioneer. He's the person who figured this all out. He's got a great professional story and a great personal story. He was born in Warsaw. He graduated from school just before the start of World War II. He joined the Polish military. He fought against the Nazis and eventually escaped to England. There he continued his studies. He received his structural engineering doctoral degree from the University of London. Eventually he immigrated to Canada and the United States and somehow ended up in Salt Lake City, Utah. He was a bit of a bookworm. He used to love to go to the University of Utah campus and check out the books, check out the library. And he was surprised to find that when he came across the section on powder flow and silo design, there really wasn't a whole lot of fundamental understanding. The design rules were pretty much based on whatever made the math easy, the fabrication easy. And for example, Engineers were really nerdy back then. Not that things are different than now, but they all carried triangles that were 30 degrees, 45 degrees, or 60 degrees. So guess what? All the hoppers were 30 degrees or 45 degrees or 60 degrees. 30 degrees in vertical was a popular choice because the sine of 30 degrees was equal to 1/2. That certainly made the math easier. So he approached the National Science Foundation and said, there's got to be a better way to do this. This is an area worth funding. So the NSF said, yes, we agree with you. This is an area worth researching, but we can't fund you because you're not a professor. So he wandered back onto campus, introduced himself to the University of Utah Civil Engineering Department, and said, do I have a deal for you? Hire me as a professor. You don't have to pay me. Just give me a lab with some students, and I'll do the rest. Come to think of it, I have the same relationship with the University of Rhode Island, where I'm an adjunct professor. They don't pay me either, but I'm able to embellish my LinkedIn profile. So it's a lot of fun. In any event, he developed what's called the Janicki Direct Tester, which is shown on the left. And since then, other more automated, streamlined testers are available. The Schultze tester, the Brookfield tester, the Anton Par tester, and the Freeman Technology FT4 from Micromeritics. When I used to work for Janicki and Johansson, Janicki offered both direct testers and Schultze testers. People ask me, what tester should I get? And I'd always say, what kind of health insurance do you have? What do you mean? Well, if you get a Janicki tester, you'll need to have good mental health coverage because it's going to drive you crazy trying to get it to work. Kind of complicated, but the Schultze tester and the other testers, they're all automated, computer controlled. They're really easy to use. So let's talk about cohesive strength. And a good analogy is a snowball. You know that if you pack a snowball really tightly, that is, if you give it a high degree of pre-consolidation stress, it's going to have a lot of strength. It can do a lot of damage. I know it because I have been the target of such a snowball. However, if you're like me, you're not able to pre-consolidate it at a high pressure, then that snowball won't have a whole lot of strength. In fact, it might be so weak it'll fail or yield on its way to the target. So my point is there's a relationship between the consolidation pressure and the cohesive strength. So we use a shear cell tester. And what we do is we apply a sample inside the cell and we shear it until it's nice and steady. This allows us to get internal friction. And then we lighten the load and we shear it until it fails. So first it's not going to move, the stress is going to build up, but finally it fails. We record that. And we do this a number of times. And eventually we can get what's called the flow function, which is the relationship between the unconfined yield strength and the major principal stress. This is just nerd language for the cohesive strength versus the maximum pressure inside the cell. So strength versus stress. And as you can see, usually the strength increases as you apply the stress. So here is a flow function, which is again the relationship between the cohesive strength and the major principal stress for a sample containing acetaminophen, Avicel, and another excipient. And you can see that, well, it has cohesion, and the cohesive strength increases slightly as you increase the stress. So by itself, it might not be too meaningful. So what a lot of investigators do is define a coefficient, a flow coefficient, FFC, as the ratio of the major principal stress to the unconfined yield strength. I like to call the flowability coefficient. It shouldn't be called the flow function or the flow factor, or FF. Remember, the flow function is the relationship between the unconfined yield strength and the major principal stress. And the flow factor is something different. I'll explain that a little bit later. So please call it FFC or flowability coefficient. Don't call it the flow function. And as a rule, people like to take the number because the unconfined yield strength or cohesive strength is in the denominator. It makes sense that a larger number means it's better flowing. And there are certain rules that people like to follow. If the FFC is less than 2, it's non-flowing. If it's between 2 and 4, we call it cohesive. 4 to 10 means the material is easy flowing. Greater than 10 is free flowing. And that's kind of dangerous because it ignores wall friction, it ignores bulk density. And plus, it turns out it's a very strong function of the consolidation stress. So if I were to plot FFC versus the consolidation stress, I see at high stresses I get a large value suggesting that this material is free flowing, whereas at low stresses it might be considered cohesive. The FFC is a lower value. So what is it? Well, it's hard to tell. And it's best not to really use it because you should use everything, which includes the internal friction. And out of a shear cell test, you get two friction angles. You get what's called the effective angle of friction, which is related to the internal friction during flow, and you get what's called a kinematic angle of internal friction, which is related to how much friction is required to get things to flow after it's been sitting. And you get the bulk density, the compressibility curve, and this is pretty typical. When you say, what is the bulk density? Well, it depends on the stress. So something as simple as the bulk density is ill-defined. You really need to measure it with a shear cell tester. So the bulk density will increase with normal stress, and you get the compressibility curve. And finally, there's wall friction, very important. So what we do to measure wall friction is we operate the tester in ways such that we place the coupon of wall material underneath a sample of powder, and now we shear it until we get nice steady flow of the powder on the wall material. We do this as a function of normal pressure, and we will plot the shear stress required to get the powder to slide along the wall coupon as a function of normal stress. And we define this as relationship as the wall yield locus. We plot the data, we get the wall yield locus, and what we like to do is we define a wall friction angle, phi prime, by drawing a line from the wall yield locus to the origin. And the angle that is formed is phi prime, the wall friction angle. So why do we want to define a wall friction angle rather than say a friction coefficient, which is the ratio? One's a tangent of the other. It's because when Janicki and others did the analysis, there were angles all over the place. There were angles that describe where we are in relationship to normal, what was normal to the wall, the Hopper angle, of course. Turns out it's a lot easier when you solve the equations to use a friction angle rather than inverse tangent of a friction coefficient. But all we need to remember is that the greater the value of the angle of wall friction, the greater the friction, the greater friction coefficient. So this is where Janicki was a freaking genius. He derived these equations that describe the direction and magnitude of solid stress in a converging hopper. And these equations were crazy. He solved them by hand. He didn't have computers. He didn't have Excel. He solved them. And they were rather laborious. He had to integrate by hand. And he was a bit frustrated at first because sometimes he couldn't get an answer, sometimes he could. And then it dawned on him that whenever he couldn't come up with a solution to these equations, it was because he could not account for the boundary condition that described flow along the walls. That is, whenever he had too high of a wall friction angle or too shallow of a hopper angle, that is, he was operating in the upper right, he could not obey the boundary condition flow along the walls. On the other hand, if he had a combination of the wall friction angle and the hopper angle from vertical that was low enough and steep enough, then he got a solution. In other words, he had conditions for mass flow. When the hopper angle was too shallow or the wall friction was too high, he had funnel flow. And the boundaries, the theoretical boundaries, are shown here, and they are functions of this parameter delta, that effective angle of friction I talked about. So now there's no guesswork. If you know what the wall friction angle is at the outlet, then you know what hopper angle is required to get mass flow. For example, if you were to measure the wall friction angle at the stress of the outlet of, say, 22 degrees, you would draw a line to the boundary and you would say, theoretically, the hopper angle that I would need to make sure I had mass flow would be, looks like 22 degrees. But again, this is a theoretical limit, so a good engineer will always give himself or herself a degree of safety and say, prescribe or recommend a hopper with hopper walls 20 degrees from vertical. Because the old line is, you know what the difference between an engineer and a scientist is? A scientist will say F equals MA. An engineer will say F equals MA plus 25% just to be safe. So we would recommend a 20-degree hopper for this combination of powder and wall material. And by the way, there's a lot of 30-degree hoppers out there, 30 degrees from vertical. And this is why they're cheap to make. So if I wanted to make a hopper, a conical hopper, walls 30 degrees in vertical, this is what I do. I start off with a square sheet of sheet metal. I would draw a couple of circles, I'd slice it in two, I'd weld together the seams, and voila, I would have a 30-degree hopper. Cheap to make. You can see there's not a whole lot of waste material. Now, if someone were to ask me for a hopper 20 degrees in vertical, I might be a little bit pissed because instead of a couple of semicircles, I have to draw this Pac-Man looking member. And now, once I fold it together and weld the seams, I will have a 20-degree hopper. It's going to be good for flow, but not very good for my bottom line, because look at all the waste material. I'd rather sell you the one on the left. Shoot, I might be able to sell you a hammer as well. I'm always looking for good ways to use wall friction. One example is the design of a transfer chute, because often you'll have, say, one device that feeds into two devices. So split it in two. And the whole idea is you want to make sure that these transfer chutes are steep enough that material continues to slide. So we start with a force balance. The acceleration is equal to the force of gravity in the downward direction, and we minus the resistant force due to friction in the upward direction. I'll need to throw in some trigonometry. The cosine theta arrives because the direction normal to the wall has a cosine in it. And we are going to define the friction coefficient as the tangent of the friction angle. And we do a little bit of rearranging, and we see that if we want to make sure the acceleration is greater than zero, that is, if we want to ensure that we have flow, all we need to do is make sure theta, this angle reference from horizontal, is greater than the friction angle, say 5 degrees to be safe. So it's really, really easy. If you want to make sure it slides, just make sure that the chute angle is greater than the friction angle. Now, I'm always looking for other ways to apply what I know. And does anybody out there snowboard? I tried. This was a rare moment where I was actually upright. I grew up in Colorado. I used to ski all the time, and I saw people snowboarding, and I said, this looks like fun. I got to give it a try. It looks so easy. I made a complete fool of myself. My nephew tried to teach me, and I just kept on falling. It was so embarrassing. I'd watch these young people just flying along effortlessly along their snowboards, and I kept on falling down. And my nephew said, "Come on, Uncle Greg. You told me that when you were in college, you used to skateboard all the time." So when we got home, I showed him the chute design equation. And I said, "See, Gabriel, there are two terms here. One's related to friction, one's related to the slope." Now, when I was on a skateboard, the friction was rather high, the slope was rather shallow, so the acceleration was rather manageable. However, when I'm on a snowboard, the friction is really low, the slope can be really high, and therefore the acceleration can be really high, and the only time it's not high is when I fall, and it's because the friction between my ass and the snow is much greater than the friction between the snowboard and the snow. Anyway, I don't know how to snowboard, but my nephew knows how to design transfer chutes. All right, more fun. Pressure distribution inside a cylinder. So we start off with a force balance. Sigma V stands for the stress in the vertical direction. Because this is a force balance, I need to multiply this first term by pi d squared over 4, the area. So stress times the area gives me a force. I also have the resistant force due to wall friction. I'll define that as the horizontal stress times the friction coefficient times the appropriate area, which would be equal to the pi d times the height of that little sliver that I'm performing a balance on. By the way, there's both a sigma h and a sigma v, because powders are what you call anisotropic. The stresses are dependent on direction. They're not like liquids where the pressure is the same in every direction. It changes depending on what plane you look at. So now I'll have both a sigma v and a sigma h. Now, these forces will be balanced by the forces from above, which will be sigma v times the cross-sectional area, plus the force due to gravity, which would be equal to the bulk density times g times the volume. So now we have the beginnings of two equations, two unknowns. We have two unknowns. We have sigma h, the horizontal stress, and sigma v, the vertical stress. But this fella named Jansen back in the 1800s, he was interested in measuring the stresses inside corn silos because he wanted to design them for structural stability. And so he took some physical measurements and is happy to notice that the ratio of the horizontal stress to the vertical stress was almost constant, typically around 0.4 to 0.6. So we can find a Jansen coefficient as a ratio of the horizontal stress to the vertical stress. And all we need to do now is substitute sigma h by k times sigma v, and with some simplification we get a first order linear differential equation. And everybody here knows what the answer is. You know how to solve a first order differential equation. You just go to Wikipedia, remember the formula for an integrating factor, and you're on your way, and you can come up with what's called the Jansen equation, which tells you that the stress, the solid stress in the vertical direction in a cylinder is equal to the bulk density times G times the hydraulic radius divided by the stress ratio, K, roughly 0.4, divided by the friction coefficient, divided by this odd term that has an exponential in it. So if we plot the results, this is what it looks like. Unlike liquids where the pressure increases linear with depth, you see that we have an asymptotic relationship for location or depth and the solid stress. It'll build up rather quickly and it'll start to decrease in its rate. And you'll notice a couple things. First of all, it turns out to be rather small compared to a liquid. For a liquid, we would have had to extend that line. For solids, the maximum stress is a lot lower. And you also notice that you get to a point where it really doesn't depend on the height anymore. It's more related to the diameter. So that's why if you ever drive past a plant, you'll find tanks and you'll find silos. And you can always assume that the tanks were used to store liquids, the silos are used to store solids. And tanks tend to be really short and squatty because you want to minimize the pressure and therefore minimize the wall thickness and therefore minimize the cost. You want to make them really short and squatty, whereas for silos, you want to make the silo as small in diameter as practical because that's what you can do to minimize the stress and make the cost of the silo less expensive. Now, in the conical section, it's a similar procedure. Again, we do a force balance, and this is what it looks like during initial fill. It's kind of Jansen-esque. It peaks up a little bit, but then it goes down as you get closer to the outlet. But now once you get flow, and this is for mass flow, look what happens. Really interesting. Again, upstairs you have Jansen, but then when you get to the interface of the hopper section and the cylinder, you get this big peak stress because things start to align differently. But then the stresses get lower and lower. Eventually you get a radial stress field down towards the outlet. So this is very important because you can imagine that the stress and strength are related. So if you get mass flow and get low stresses at the outlet, then you get low strength at the outlet, and chances are good you'll be able to get away with a smaller outlet to prevent a flow obstruction. So one last concept. Talk a little bit about arch supporting stress. Again, we rely on simple physics. If we were to do a force balance on the stress on the abutments of an arch, it'd simply be equal to sigma 1 bar, the stress on the abutment of an arch, is equal to the bulk density times G times the span, divided by approximately 2. If this were a nice perfect arch, then it'd be exactly 2. But Janicki did some measurements, found out it was a little bit smaller, so he defined a function h of theta prime being the hopper angle. And so it's going to be approximately 2. 2 plus change. The amount of change depends on the hopper angle. So now we're getting there. Again, this is the pressure distribution. We're able to calculate that if we know what the bulk density is and what the wall friction is. And if we were to measure the cohesive strength over a range of pressures, we would have the flow function that would allow us to know what the consolidation stress is, what the cohesive strength is as a function of the consolidation stress. So now we can plot everything together. We can calculate the amount of strength a powder has at any location inside the hopper. Now remember, I showed you that the arch supporting stress is proportional to the span, proportional to the diameter. So if I were to plot the arch supporting stress on the same graph where I showed the cohesive strength as a function of position inside my bin, then I can see there are two scenarios. If the diameter is large enough, the stress on the material is greater than its cohesive strength, and that diameter is large enough to prevent a flow obstruction. On the other hand, if my diameter is too small, then the strength is greater than the stress. That means the diameter is so small, the arch that forms is going to be stable because there's not going to be enough stress on the material to cause that arch to fail. So there's a point there where the stress and the strength are equal. Recall that the arch supporting stress is equal to the bulk density times G times B divided by shape factor, roughly 2 for a cone. All we need to do is substitute this critical stress for the arch supporting stress, do a little rearranging, and we get a very simple relationship that tells us what size the hopper outlet has to be to make sure we don't get an arch. It's equal to the shape factor, roughly 2 for a cone, times the critical stress divided by the bulk density times G. And it's really elegant and makes a lot of sense. It follows our intuition. We know that if a powder is cohesive, that critical stress is probably going to be high too. Therefore, the calculated value of the minimum arching dimension is going to be large. And what's more subtle, but it makes sense, if you have a material that's really heavy, if it has a high bulk density, that's going to be a lot of weight on that arch. It seems like it'd be much easier to get that arch to fail, even if it has a small diameter. So sure enough, the bulk density term is in the denominator. So Janicki made it even easier. The flow function, again, is the relationship between the major principal stress and the cohesive strength. And the flow factor was defined as the ratio of this major principal stress to the arch supporting stress. What he found was that the equations that describe the stress profile in the hopper section were a little bit unwieldy, unlike the equation that described the arch supporting stress. But they all had the same terms, the bulk density, they had G, and they had diameter. So he divided one by another, came up with a more or less a dimensionless group he called the flow factor. Again, it is the ratio of the major principal stress to the arch supporting stress. And shown here is what Johansson defines as a critical flow factor. And it's a function of the effective angle of friction, which again we're able to get out of a shear cell test. So now it's a lot easier because again, once we've measured the flow function, that is, we measured the cohesive strength as a function of consolidation stress. Now we can plot the flow function on the same line as the flow function. And again, we have two scenarios. On the left, shown in green, the flow function is above the flow factor, which means the cohesive strength is greater than the arch supporting stress. That means the diameter is not going to be large enough to cause that arch to fail. Whereas on the right side in yellow, the flow factor is above the flow function, which means the stress is greater than the strength. A outlet diameter of that size would be large enough to cause the arch to fail. So just as before, we use that easy equation, the critical outlet dimension required to prevent an arch from forming is equal to the shape factor, roughly 2 for a cone, times the critical stress divided by the bulk density times G. And now we don't have to calculate the stress profiles inside the hopper. Janicki has done that for us. It's implicitly given to us in the flow factor. So let's do an example. Let's say we have an existing hopper. These are one of the cheap hoppers you got from Hopper Depot. 30 degrees from vertical, 60 degrees from horizontal. And we have 100 millimeters, I think that's 4 inches. I always say there's two types of units, metric units and units used by the only company in the world to have ever landed a man on the moon. But this is a typical hopper portable bin that you will find in pharma. And the question is, will my formulation, the blend that I showed you earlier, will that flow reliably in this bin? So again, I've measured the flow properties. I have the flow function, I have the compressibility curve, I have the internal friction, and I have the wall yield locus. And according to the FFC calculation, at least at high stresses where people tend to measure everything because it's easier to discern between different values of FFC for different powders, it's easy flowing. So we might be optimistic that this is going to do well. So now we go through Janicki's procedure. The last step is we measure the wall friction angle at the outlet pressure. We see that's 31 degrees. From that, we're able to calculate the recommended mass flow hopper angle, which is 9 degrees. It's going to be ugly, but it is what it is. We're able to calculate the flow factor knowing the effective angle of friction, which is about 1.332. We plot the flow factor together with the flow function. We get a critical stress. We're able to plug that into Janicki's design equation, and we see that we get a 240 millimeter outlet. And to get mass flow, we would need a 9 degree from vertical hopper. That's one ugly hopper. And by the way, this calculation is for mass flow. We have funnel flow because our hopper angle is much greater than 9 degrees. So we have a similar calculation for arching in a funnel flow hopper. Bottom line is, even though we had an FFC of 7, which says it's easy flowing, this material will not flow. So what do? Well, we add fumed silica. And I recommend Cabicil M5P fumed silica because it's a shameless plug for my old employer, Cabot. I still own Cabot stock. But if you add a little bit of fumed silica, the way fumed silica works, it acts as a parting agent. You have these small particles of silica between the larger particles of powder. And so you create distance between these primary particles, and as a rule, the cohesive forces between particles depend on the distance, so the greater the distance, the less the strength. So you can see that if we add just a little bit of fumed silica on the order of 1/4 of 0.5%, we reduce the cohesive strength. We lower the flow function rather dramatically. And we also, and this isn't always the case, we also reduce the wall friction. We see that the wall yield locus, when we added a little bit of Cabicil, the wall friction angles are going to be dramatically lower than that of the control where we didn't add any flow aid. So now we can go through the same routine. First of all, we calculate the FFC. Hey, it's equal to 10. Free flowing, it's got to work this time. And we get a critical arching dimension of 100 millimeters, which is right in line with what we have. But unfortunately, the required mass flow hopper angle is 22 degrees from vertical, and our hopper is 60 degrees. So, well, it's not hopeless. Funnel is not bad as long as it doesn't form a rat hole that's stable. So that's another calculation. So again, if we know the bulk density, we know what the wall friction is, we'd be able to calculate what the stress profile is inside our funnel flow hopper. And unlike before, the stresses aren't going to be reduced at the lower section just because things aren't flowing, at least not along the walls. So we have a rather high solid stress throughout our hopper, especially at the bottom. Again, if we have measured the cohesive strength as a function of stress, using the flow function, we now know what the cohesive strength profiles inside our bin. And Janicki came up with another concept. He came up with a relationship that described what we call the flow channel stress, which is equal to the bulk density times d, the diameter of the outlet, divided by a factor g, which is related to phi, this other internal friction I talked about that we get from shear cell testing. Now we can compare the flow channel stress with the cohesive strength. And you can see for this diameter, upstairs, some of the material has a strength that's less than the flow channel stress. That is, the stress on the rat hole is greater than the rat hole's cohesive strength. And so up there, the rat hole's going to collapse. But further down, we have the opposite. The strength is greater than the rat hole stress. The stress on the rat hole is not as great as the cohesive strength. So down there, the rat hole will remain stable. So how do we make sure that the rat hole is unstable everywhere so everything empties? Well, sometimes we need to have a really large outlet size. So in this case, we can view the similar calculation, and we will calculate what we call the critical rat hole diameter. Plugging in the numbers, we see that the diameter required to make sure that the rat hole collapses everywhere because we have funnel flow is equal to 150 millimeters, which is bigger than the outlet that we have in our hopper. So this is not going to work. It might not arch, it's not going to arch, but we are going to have a steel rat hole. We won't be able to empty the entire bin. So when you compare the relationships that gives us the critical outlet dimension to prevent arching in a mass flow bin with the critical rat hole in diameter that's required to prevent a stable rat hole from forming in a funnel flow bin, you can see how different the results can be. For mass flow, you can see that the stresses are smaller at the outlet, and so that critical stress is really small. And the shape factor H is roughly equal to 2, and you divide by the bulk density, you can get a pretty small number, versus if you had funnel flow, and you calculate DF, this factor G is on the order of 3 to 4, which is greater than H. The value of the cohesive strength is the maximum strength of the rat hole, which is what you calculate for the stress given by the Janssen equation, again divided by the bulk density. So you can see that can be a rather large number. So that's why you often want to have mass flow. The required outlet size to prevent a flow obstruction, that is an arch, can be rather small. Whereas if it turns out if you have funnel flow, the size of a hopper outlet required to prevent a stable rat hole from developing if your material is cohesive, it can be bigger than Kim Kardashian's ass. So more often than not, you want to have mass flow. But fortunately, we have one more level. We can add some stearate, magnesium stearate. Magnesium stearate acts as a lubricant. So you see that if we add some stearate, first of all, it acts as a free flow agent to some extent, so we're able to reduce the flow function as well. And shown on the right side, you can see that we dramatically reduce the wall yield locus. The wall friction goes lower. And so now if we were to perform Janicki's analysis, first of all, the FFC is equal to 15. Man, this is great, really free flowing, but that doesn't really matter. What's really important is now our critical arching dimension is 50 millimeters. It's not going to arch. And the recommended mass flow hopper angle, that is the minimum hopper angle from vertical that we would recommend to prevent a rat hole from forming in the first place and make sure we have mass flow, is equal to 36 degrees. That hopper that we got from Hopper Depot that has this 30-degree from vertical wall, it'll work just fine. So we win. So to summarize, flow properties include cohesive strength, internal friction, compressibility, and wall friction. Cohesive strength, internal friction, compressibility allows you to determine the size of a hopper outlet required to prevent an obstruction to flow from developing. And wall friction, of course, tells you what hopper angle you need to prevent rat holes and allow mass flow. So the best flowability metrics, I wouldn't use FFC or car index or Flodex. What I recommend people do is start tabulating arching diameter, rat holing diameter, and the required mass flow hopper angle. Put these three metrics into your spreadsheet, and you will be able to have proper definitions to predict flow behavior in existing bins. So please, do not use FFC. I really believe that anybody has a shear cell tester and knows how to conduct the proper tests and perform the right analysis should not have a powder flow problem. So I know I went rather quickly, but I invite you to go to my website, www.mihos.net, and from there you can actually download the spreadsheets that I use to take the shear cell test results and determine the critical arching dimension, the rat holing dimensions, and the recommended mass flow hoppers. It's fairly easy to use. I have some VBA-driven macros, and once in a while you might get an error. And I tell people it's not a bug, it's a feature, because when you get an error, it's usually because your material is so cohesive, gravity flow is not possible, or your material has such high wall friction, flow along the walls, mass flow is unlikely at even very, very steep hopper walls. And you can also go to my website and download my textbook on bulk solids handling. There is a free download there if you wanted. You can purchase a paperback which has a little bit more information as well, but the one that you can download from a website has just about everything you need. And I suggest you first go to the final page, which is titled Better References than this one. You can almost see in my background my library. I have lots of good books. There's lots of good stuff out there. And it's a fascinating topic. And again, it's really, really easy, overly easy. If you think about it, if you want to make sure that material flows through the outlet of a hopper, just make sure it's big enough. If you want to make sure it flows along the walls, make sure that the walls are steep enough. So you measure wall friction, you measure crease strength, and there's some rather simple equations that tells you whether or not your hopper is going to meet its purpose, or tells you how to design a new hopper that will allow reliable handling. So take care.